Hello, my name is Joe Cloud and I'm with NASA's Kennedy Space Center. On behalf of my co-authors, I'm presenting our work on hazard detection in the lunar South Pole lighting conditions. Due to the high cost of launching materials to the moon, future missions will leverage resources found in situ. This is referred to as in situ resource utilization, or ISRU. This means processing lunar regolith to extract valuable minerals like oxygen. The lunar South Pole is a primary target because its permanently shadowed regions, such as the craters, contain water ice, a critical resource for sustaining a human presence. To harvest these resources efficiently, NASA is developing autonomous excavators that must navigate the terrain while maintaining high operational efficiency to excavate enough regolith to supply ISRU processing plants. One such excavator is depicted here, which is ISRU Pilot Excavator. It features several cameras used for navigation. These robots face unique challenges, however. At the lunar South Pole, the sun never rises more than a few degrees above the horizon, creating extreme lighting conditions with long shadows and blinding glare. This image shows an example of down-sun driving from the perspective of the robot, where the robot moves away from the sun. Its own shadow extends far ahead, potentially including hazards. Note that the unfiltered sunlight creates extreme contrasts. The vertical rock faces normal to the light are brightly illuminated, while shadowed regions appear to be very dark. At these low angles, rocks can cast shadows that are several meters long, making it difficult to distinguish actual hazards from their shadows. Also challenging, when driving in the up-sun direction, directly into the light, camera sensors struggle with dynamic range, similar to driving into a sunset but more extreme due to lack of atmospheric attenuation. Replicating these conditions terrestrially for hardware testing is challenging, which is why accurate simulations become essential for developing robust vision algorithms. To address this and other work, we developed a high-fidelity simulation based on the Unity high-definition rendering pipeline to mimic environmental conditions anticipated at the lunar South Pole. We created imagery at 3 specific solar angles, including 2.5, 5, and 7.5 degrees, representing different times throughout lunar day. We simulated both up-sun and down-sun driving and collected auto-annotated data for each sequence. Each presents different challenges. The rocks are procedurally generated and placed based on lunar rock distributions based on known surveyor block distributions. The virtual camera is modeled after a Sony IMX264 sensor with specifications matching those of a previous iteration of the ISRU Pilot Excavator. We generated a comprehensive data set with over 83,000 individual rock annotations. The training set consists of 960 images at 5 degrees solar elevation, while our test sets cover all 3 angles and both driving directions. We use a unique rock distribution and shape seed for our training data. As the rocks are unique to the training set, they do not appear in the test sets at all. We evaluated 3 state-of-the-art instance segmentation approaches, Mask R-CNN, YOLOv8, and the Segment Anything model, or SAM. Each was trained on our synthetic lunar imagery, with the exception of SAM, which we developed a custom filter approach since it performs zero-shot instance segmentation. Our filter in this case identifies a horizon line and then uses terrain structure to isolate rock hazards from other features. This process is further described in the paper. Looking at the results, you can see how each model performs differently across different lighting conditions. The top row shows down-sun driving at increasing solar angles from left to right, while the bottom row shows the up-sun direction. With Mask R-CNN, we see decent performance at higher sun angles, but it struggles with smaller rocks and harsh shadows at 2.5 degrees. YOLOv8 shows the most robust performance, successfully detecting partially occluded rocks even in challenging conditions. Notice, however, it maintains good detection in the difficult 2.5 degrees up-sun direction as well. SAM, while showing consistent behavior, tends to include shadows in its segmentations and misses smaller, distant rocks. Our quantitative analysis confirms these visual observations. YOLOv8 achieved the best performance with map scores ranging from 0.71 to 0.89, while maintaining fast inference at 30 milliseconds per second, suitable for real-time operations depending on the compute available. Notably, YOLOv8 also showed the smallest performance gap between the up-sun and down-sun scenarios. Mask R-CNN showed moderate performance with the steepest improvement curve as solar angles increased, while processing at a much slower 120-170 milliseconds per frame. SAM, despite its flexibility, had the lowest accuracy and slowest speed at nearly half a frame per second. The unsurprising finding is that all models perform better at higher solar angle elevations, with the 2.5 degree up-sun scenario being the most challenging across the board. As we prepare for future ISRU missions, we are exploring new means of improving the autonomous capability of our excavation platforms, including a terrestrial test site at Kennedy Space Center that enables us to test the hardware under similar conditions. For more information about these efforts, please check out the website at nasa.gov/ISRU-pilot-excavator. Thank you for your attention, and I'd be happy to answer any questions sent to me.